Okay, hi everyone. This is Dan Barry from NOAA in Silver Spring, Maryland, and we're going to get going with today's webinar. The topic of today's webinar is high-resolution modeling, working toward improved process representation and simulations of the Earth system. I'm very excited for the 6 speakers that we have joining us for the webinar today. We're going to first hear from Jim Kinter from COLA, then Justin Small from NCAR, Eric Swenson from George Mason and COLA, Francisco Douglas-Reyes from the Barcelona Supercomputing Center in ICRIA, Lucas Harris from NOAA GFDL, and Ben Kurtman from the University of Miami. It's an interesting webinar. We're going to have kind of a number of talks that cover both high-level science issues as well as more focused scientific topics. So there's a really nice diversity in terms of the talks that we're going to hear today. And we're doing something new for this webinar, so we have a new trick up our sleeves here. We want to keep everyone awake all the way through the webinar and engaged all the way to the end. So we're actually going to ask poll questions as we go along here of the audience. And there are a number of questions related to essentially the effective resolution on both prediction skill and model fidelity. So we're going to be thinking about both subseasonal to seasonal forecasting with these questions, but also CMIP6 context. These are totally anonymous questions, so your name will not be associated with your response, so feel free to answer as accurately as you care to. And we're going to have 4 of these questions. They'll be distributed throughout the webinar between the talks. We'll probably just spend about a minute or two doing the polls as we go along. And I wanted to start out really quick with one poll in the beginning, just to make sure that everyone is able to do this. So it's kind of a tester. So this is a very simple one. I'm going to open the poll right now, and the question is just, can you see, respond to, and submit your response to this poll question? And I see that we already have about 7 people in progress, and about 10 people have finished, so people are doing really well with this. Everyone is saying yes, which is great. That would be sort of disturbing if some people were saying no in response to this question. Still about 20 people who have not started the poll yet, so if you don't mind jumping in and giving it a shot. And we have a number of folks who are still filling the poll out, so we'll keep going for a little bit until it seems like we've reached an equilibrium. And basically, it's just, we're just doing an interesting wisdom of the crowd experiment here. The people who are logged into the webinar have varying levels of scientific expertise and expertise in different areas. So, this is not necessarily an expert assessment of the response to these questions, but it's just a sense of where the community that's logged into this webinar, at least, thinks the answers to these questions are. So, yeah, we'll spend about 1 or 2 minutes on each of these questions. I see people are still jumping in and trying to answer the questions. So we still have 3 people who are considering. Somebody actually did say no, so that's interesting. I would love to talk to that person after the webinar is over. And give it just a few more seconds while people finish up. Okay, so I see there are 3 people who are in progress, so maybe you haven't actually submitted the poll yet, so just check to see if you have submitted the poll. If you haven't, feel free to go ahead and just submit it. But I'm going to start closing it now. The poll will close in 17 seconds, so you have 16, 15, 14 seconds left to submit the answer. And in the meantime, I'm going to pass control over to Jim so that he can share his screen with us. Okay, Jim, you should have control now, so if you don't mind going to the Quick Start tab and then sharing your screen, that would be great.
Can you see it?
Yeah, it looks great. And I just shared the final poll results with everyone, so you can see how these are going to come up when the results are in. And you can adjust the column width so you can see the results better. But 33% did not answer the question. 36 out of 55 attendees said yes, they could see, respond to, and submit the poll, and 2% or 1 person said no. So that's how the results will come up after we do the polling questions. And what I'm going to do is show all the results at the end of the webinar, so you have to hang on until the very end of the webinar to to see what the community thought about each of the questions. All right, Jim, whenever you're ready, go ahead, take it away.
Great. Well, thanks very much, Dan. Thanks also for organizing this webinar. What I have to say in just 12 minutes is not particularly profound, but I'm hoping it will lay some groundwork for the excellent talks that are going to follow. So first thing, let me get this thing, there we go. First thing to note is that when we're thinking about the problem of seamless prediction, which Dan teed up for us a few minutes ago, all the science questions that you might be considering asking, particularly if they have to do with predictability, are both model and resolution dependent. And I've just put a couple of examples up on the screen here. What limits predictability at all timescales is, of course, a very generic question, something that we've been thinking about at COLA for many years. There have been recent papers. Sandrine Bonny and company just a couple of years ago produced a set of fundamental questions for climate science, and if you look at the questions that they posed, they all have model and resolution dependencies. Hawkins and Sutton, talking about climate change and how to detect and attribute the response to climate change, identified a number of sources of uncertainty in the system, and if you look at those, they also are all very much dependent on what sorts of resolutions our models have. And then finally, if you really drill down and think about models, model error, what is the optimal resolution, what is the optimal ensemble size, if you're trying to predict either means or extremes or some other part of the probability distribution, again, the model dependency is obvious. So when we think about models, resolution, and computing, we have followed two paths historically over the past, say, 50-plus years. One path looking at numerical weather prediction, strictly thinking about how to make forecasts for the next couple of days. And of course, here in the Washington and mid-Atlantic New England areas, we're very critically focused on the weather forecast today because there is a winter storm warning for the DC area and a blizzard warning for New York and New England. So this has been one track. The other track has been what I'm going to call for this talk, numerical climate simulation prediction, which both of these depend critically upon high-performance computing and what I'm going to call big data, just to go with the vogue for that kind of terminology. I know that a lot of people don't like the name big data, but the idea being we need both capability and capacity for computing and for data management. If we think about the history of high-performance computing and how we might have exploited it, well, the beginning, the dawn of our digital computing age was ENIAC in the mid-1940s, and the latest and greatest is a machine called Titan sitting in Oak Ridge National Laboratory. It's about 7 decades in between those two. In 1946, the state-of-the-art was 357 floating point operations per second. Those are 10-digit multiplied by 10-digit multiplies. And it was the beginning of stored programming. Here in 2016, when Titan was deployed, the peak speed is 27 petaflops, which is delivered on almost 300,000 cores. ENIAC, of course, just had a bunch of registers. What have we done with this accelerating high-performance computing? Well, on the NWP side, we've made enormous progress, primarily through increasing model resolution. You could argue that we have done quite a lot of work about representing relevant processes, particularly convection, and we've also made enormous advances in data assimilation. But in terms of the computing side of things, it's increasing model resolution that has driven the boat, and it is increasing model resolution which has added, I will argue, the most to our capability at NWP. On the numerical climate simulation and prediction side, we've made much more modest advances in spatial resolution, and instead we've absorbed all of those many orders of magnitude of computing power through new components and processes. So in 2008, there was a World Climate Modeling Summit. It was held in Reading, UK, and that meeting called for an exploration of dramatically higher resolution climate models, the thinking being that by containing ourselves to modest resolutions in climate models, we were actually limiting our ability to do what we needed to do. So let's think about spatial resolution for a minute. We think about increasing spatial resolution in numerical models because we expect the numerical solution of partial differential equations to converge to the continuous solution as we refine the grid. And that basically means we're reducing or eliminating the approximations we have to make as we solve these equations. But then the question comes up, how much refinement is enough? We don't have closed form solutions for the continuous equations. It's not practical and it's probably not scientific to try to attempt to track every mole of substance in the Earth system. And on the other hand, if we think about global average models or box models or even 100-kilometer coarse resolution climate models that are only tracking the larger scale features, we've discovered that those are clearly inadequate for some of the things that we need to know. So the next question is, between these two extremes, tracking every mole and tracking just the global mean, where are the breakpoints or the thresholds where we can gain some traction in our models? So there's also some practical matters to think about. There may be relatively better improvement if we concentrate increasing resolution on the atmospheric side, on the ocean side, and the land surface, or other aspects of the climate system. We have to be cognizant that there are numerical solution issues, and I just listed one of them here from a paper by Lindzen and Fox-Rabinovich from many years ago, where they pointed out that wave propagation in the atmosphere is sensitive to the aspect ratio of vertical to horizontal resolution. We also have the issue that as we go to higher resolution, our models will start to produce new features that we weren't necessarily prepared to deal with. And I just give one example here. As we go to ocean models with very high resolution that are eddy permitting or eddy resolving, now suddenly we have multiple ocean grid points at the mouths of large rivers, and the question is, well, where does the runoff go when we couple the land surface model to the ocean model? And that actually introduces issues with freshwater lensing and potential instabilities in numerical configuration. And then finally, we have this practical issue of trade-offs. And I've showed this figure many, many times in many, many places, and now I see other people showing it. So I've succeeded, I can retire. But anyway, the idea is that we think of a multi-dimensional space where we have atmospheric resolution and land surface resolution on one axis, ocean and sea ice resolution on another axis, statistical resolution, which typically we do with multiple equally probable ensemble members. But piercing this space as a sort of a plane, as it's represented there with all the little ones and zeros, is our potential curve. It's a surface where the computing resources are limiting us. And if we increase resolution in one of these axes or increase the number of ensemble members, we have to give up something in one of the other dimensions just because computing time at computer resources at any given time are always limited. So as we get to this point about thinking about what we resolve and what we don't resolve, we inevitably end up with the question of parameterization. So anytime we do a discretization or a filtering of our equations, we implicitly or explicitly discriminate between what's resolved and what's not resolved. And by resolved, I mean features that have a size of anywhere from 5 to 10 grid lengths in our discrete models. But we know that the rectified effects on these unresolved scales are quite important even on the resolved scales and can be even first order. And this is because the system is nonlinear, because there are irreversible processes, because there is increasing entropy in the system, and so on. So we parameterize. We represent the rectified effects, the unresolved scales. On the resolved scales, the parameterizations that we use are generally local, meaning they don't necessarily know about far-field effects. They're diffusive, meaning they tend to go down gradient in energy, and they are generally in the direction of restoring equilibrium rather than disequilibrium. And that means that they don't adequately represent processes that are non-local or that are up-gradient or that are locally unstable in space or time. And of course, the reason for that is that if we wrote parameterizations that had those properties, they would be unstable numerically and we wouldn't get solutions. So, and I've just given a long list. I'm not going to walk through this in the interest of time, but I think everybody is familiar with some of the things that we have traditionally parameterized when our climate models are order 100-kilometer grid spacing. We have to parameterize clouds. We have to parameterize turbulence. We have to parameterize microphysics within the clouds. We have to parameterize ocean mixing. We have to parameterize a number of small-scale features in sea ice. There are parameterizations associated with the non-local effects of coupling, with the with sea spray as a source of cloud condensation nuclei, and then there are processes that we're only beginning to put into the models like dynamic vegetation and biogeochemical cycles. So all of these represent crude approximations at best, and our hopes of trying to resolve some of them are what we're working on today and what you'll hear about in some of the talks that are coming up. Now, I want to end with just talking about how we're approaching this transition from, at the top of the screen, the global climate models of order 100-kilometer grid spacing, in which we fully parameterize lots and lots of things. We've seen two paths forward, one which David Randall calls the do-nothing approach, simply changing the card in your deck if you're an old guy, or the parameter in your run script if you're moderately less old, of what the resolution of the model is. That's the right-hand path, the Meso-Global models, where we just take our delta X of 100 kilometers and we increase the resolution to something like an order of magnitude better. The other path, which Randall and company have been going down, is this multi-scale modeling framework, or superparameterization, where they embed full up models that are not parameterized inside the large-scale models. In this case, they parameterize a column model of cloud, convection, and everything else is parameterized as usual. Our goal down here at the bottom, at least our immediate goal in the next decade or so, is to try to get to models where we're resolving clouds and ocean eddies and all of the things at about the same scale, around 1 kilometer, still having to parameterize turbulence and cloud microphysics. So when I look at this Meso-Global models over here on the right, which is simply increasing resolution without necessarily reinventing parameterizations, here we're resolving all of the things that are mesoscale, things like tropical cyclones, extratropical cyclones, ocean eddies, at least we're permitting ocean eddies, catchment scale flows of water and other things, and ice flow distributions. We're still parameterizing subgrid physical processes like convection and ocean mixing in these models. But these are the sorts of models that we actually have to be working with today. There's tremendous societal demand for information at these scales, the 100-kilometer scale not being particularly sufficient for a lot of applications. When we think about doing seamless prediction from days to decades, again, we have to have the weather represented, the mesoscale features represented quite well. We have process scale interactions that are better represented as we start to resolve the mesoscale. And finally, if we want to assimilate data at the scale that the observations are taken, we're thinking about the same sorts of scale models. So I just want to give a couple of quick examples, and these are all examples that our group at COLA has been involved in. One was this Project Athena, where we collaborated with the European Center to run the atmosphere, the IFS, at varying resolutions. And just very quickly, what you're seeing here is a number of regimes in extratropical atmospheric circulation, and they all have names that I'm not going to go into, but if you look at the middle row, the ERA interim row, that's our target. The bottom row down here, T159, is about a 100-kilometer global model, and you see that there's very little correspondence between the sorts of patterns we see in circulation regimes in this low-resolution model and the observed regimes. But when we go to a 16-kilometer global grid, we suddenly see all of these regimes coming into sharp focus and quite well reproducing both the structure and the magnitude distributions of these patterns. Another example from a project that we did collaboratively with NCAR and Ben Kurtman, who's going to give a talk later, is this PETA-APS project, and I'm sure Ben will talk about this, but here we ran the CCSM, the NCAR community model, at two different ocean resolutions, one 1 degree ocean global grid and the other at a 1/10 of a degree ocean global grid. And what you see is our target for rainfall distribution in the North Atlantic is down there at the bottom, where you see this sharp gradient of rainfall sort of associating itself with where the Gulf Stream and Gulf Stream eddies are. Here is the simulation at the low resolution and contours, and you see we're failing to reproduce the distribution and magnitude of the rainfall, but the color contours up here are with that ocean eddy resolving version of the model, and suddenly we start getting a very realistic simulation of the mean field in the atmosphere, even though the resolution was enhanced in the ocean. Last example, again, this is now coupled forecasts where we're initializing with real initial states, and this is a paper from Julia Manganello. And what you're seeing here at the top is observed values of distributions of tropical cyclone track densities. Just look at the left-hand side, the North Atlantic. We see these two big regions in the observations, and as we go from moderate resolution to higher resolution to very high resolution, 16-kilometer global grid in this second row here, we see an increasingly realistic representation of the distribution, even overdoing it a bit off the coast of North America. And then I wanted to also point out that here we get much better correlations looking at the accumulated cyclone energy forecasts as we both increase resolution, which is going from the green up to the blue and the red, and also we see this improvement as we go to higher, larger ensembles. And I haven't talked about that, but that's another aspect we have to keep in mind. So this is my last slide. Just wanted to give you a flavor for where we are in terms of thinking about how to go to higher resolution. We have found that increasing spatial resolution helps in a lot of ways. It helps with blocking and other topographically oriented features. It helps with this scale interaction of mesoscales and large scales, but it is not a panacea. We still see some of the ubiquitous and lingering nagging mean errors in our models don't get that much better when we go to higher resolution, and it's an interesting science question. Why not? If we are increasing resolution, we should be converging to the continuous solution, but we are finding these nagging problems. Why is that? And that goes with the second point here. We see threshold behavior where as we increase the model, particularly of atmospheric models, from 100 to 50, and then we suddenly see that we don't get much improvement beyond that. And there's an interesting question. Is that because the parameterizations are tuned to those coarser resolutions and we can't push forward? There's been a lot of work on what are called gray zones, which is places where parameterizations are no longer appropriate. The assumptions associated with them are not appropriate. And I'll just give a couple of examples there: a global atmosphere in that 4 to 10 kilometer range, and as we go to boundary layer and clouds, where 1 kilometer, and for ice flows, again, 10 kilometers. And this is where a lot of work is being done today to try to develop parameterizations that are actually aware of this and change their assumption base as we go to higher resolution. There is quite a lot of long-term bias that can be ascribed to what we call fast physics, and we can show that by doing initialized forecasts as they've done in the CAPT set of experiments. But some biases take a long time to develop, and it's interesting to try to understand why that is. There's quite a lot of work going on missing physics, and Tim Palmer and company have been arguing in favor of shifting to stochastic parameterizations, just to acknowledge that some things are unpredictable at small scales, and they simply have a rectified effect, which we can model statistically. Last 2 points: traditional diagnostics that we've been using don't necessarily help us identify and understand errors in our models because they aren't process-oriented diagnostics. And there's been some work, Eric Maloney and others have been pushing this idea of process-oriented diagnostics that we can use to better attribute what the source of errors are in our models. And finally, our observing systems are delivering very high-resolution data today. We now have GOES-16 that will be delivering data soon that's going to have unprecedented resolution, both in spectral space and in spatial resolution. Are we doing what we need to do to extract all of the information from these types of observing systems in order to initialize and validate certainly Meso-Global coupled models, but then eventually global cloud and eddy resolving models? And I'll be happy to take questions.
Great, thanks so much, Jim. So for those who are logged in virtually, the way to ask a question is to send me a chat message and let me know that you have a question. So you can find the chat option. If you go to the top of the screen, it says viewing Jim Kinter's screen. You can click the chat box, and then you'll be able to send me a chat message, and I can unmute your line and allow you to ask your question. So we'll wait for a moment to see if any questions come in. So again, go to the top of the screen, hover over viewing Jim Kinter's screen, click chat, and then send me a chat message, and I can unmute your mic and you can ask a question. I think, Jim, in the meantime, I may actually open the poll up. You've done a really nice job prefacing the first question that we were going to ask. So I'm going to go ahead and open the poll, given that I haven't gotten any questions yet. So hopefully everyone sees this question pop up on your screen. I'll read the question. It says, in the computationally limited trade-off space between the areas below, which area holds the most promise for improving the skill of seasonal forecasts? And there are 5 options, A through E, so please, choose which one you most agree with. Jim showed that slide early on and discussed this a little bit in his talk, so I think primed some of the responses that we may see. For those who joined since Jim started, we are doing polling in this webinar for the first time. We had about 20 people join the webinar since we did the test poll. So, just do your best to answer this question. These are tough choices and trade-offs, but just do your best to choose one of the items. And what we're going to do is do 3 more of these between the talks, and then we'll discuss the results at the end. So we won't show the results until the end. So just choose your option, click Submit in the bottom right-hand corner of the window, of the polling window, and then we'll tabulate the results. So again, if you have a question for Jim, please use the chat feature in WebEx. Again, you go to the top of your screen, hover over the Viewing Jim Kinter's screen, drop down, and then a menu will pop up, and you can click Chat and then send me a chat message if you have a question for Jim.
So Dan, while people are doing that, I just put this fun picture up on the screen. I'm sure a lot of people have seen this. This is a picture of ENIAC, and there's 2 things to like about this picture. One is that the programmers are women, and as it turns out, it used to not be the case that computer science was dominated by men. It used to be women who were the programmers. And the other thing that's fun to note is, excuse me, that machine delivered 357 floating point operations per second, and it was used to produce, excuse me, numeric weather forecasts. The first one of those that actually got done before the weather was verified was in 1950. So we've had just over 65 years of numerical weather prediction. Just fun fact.
That's really cool. Yeah, thanks for sharing that. It's neat to see this photo. My grandmother-in-law actually was one of the programmers who worked on ENIAC. We found out recently she was a mathematician at the University of Pennsylvania back in this era, and so she was one of the programmers. We've never managed to find a photo, though, that has her in it, unfortunately, but that's really cool to see that photo. Thanks for sharing that. Okay, so we've gotten a lot of results from the poll. There are still 33 people who haven't taken it yet and a couple people finishing it. So I'm going to click Close Poll now. So you should jump in there and get it started. You'll have 20 seconds from the time I click Close Poll to go ahead and submit your result. So I'm going to click it now, and it's counting down. So if you haven't yet submitted your response, please do it in the next 8 seconds. And I haven't seen any questions yet through the chat feature, so I think we'll just jump to the next speaker. But Jim, thank you so much for the presentation. That was really interesting and a nice overview to the topics we're going to be discussing today. Okay, so the next presenter is Justin Small. Justin, I'm going to pass control over to your computer now, and you just go to Quick Start and then share your screen, and then bring your slides up.
Okay, I hope you can hear me and see my slides, Dan, and
yeah,
everyone.
Looks great, Justin. Thank you. So whenever you're ready, please go ahead. Okay,
so I'm going to talk about efforts at NCAR and also the university community of UCAR on high-resolution modeling, also some aspects of data assimilation. That'll be very short, with the community Earth system model. So as well as myself, I've had input from Fred Castruccio and Steve Yeager, Alicia, Gökhan, and Frank at NCAR. And I'll mention right at the end the ESM3 project with Ben Kirkman regarding the data assimilation. So the outline of the talk, I'm going to discuss how changing model resolution in the community Earth system model changes some aspects of the mean, climate, and variability. And I'll try and divide it into sensitivity to atmosphere resolution and then sensitivity to ocean resolution. And I'll briefly point to the data assimilation methods, and I think it's possible that Ben will talk more about that later. The community Earth system model, some people will be familiar with this, but the main components I'll be talking about in this talk are the ocean, that's the Parallel Ocean Program POP model, and the atmosphere, the community atmosphere model, CAM. And I'll use two versions of that, CAM4, that was primarily used in the old community climate system model, version 4, CCSM4, some people will know of, and then CAM5, which is used in the early versions of the community Earth system model. And I'll just point out now there's a big push to develop the community Earth system model, or CSM version 2. That's a big effort, a big kind of university and NCAR-wide effort with many changes to CAM, towards CAM6, the LAM model, the sea ice model, and also the coupling infrastructure. But this is very new work. It's in progress, and I won't discuss it here. I'll also point out I'm not going to be using the glacier or land ice model or ocean biogeochemistry, which are features of the main CSM. The resolutions I'm going to discuss in this presentation primarily for the atmosphere, the CAM5 model, are 1/4 degree and 1 degree. You can see them on the top row of the table here. And then the ocean resolutions are the 1 degree, which uses parameterizations of ocean eddies, and the 0.1 degree, which resolves a lot of the eddies. And our highest simulation is shown here in red. We had 100 years of the high-resolution atmosphere and ocean. We had a slightly shorter run with 1 degree atmosphere, 1/4 degree atmosphere and 1 degree ocean. And then we had a longish run of the standard resolution of 1 degree in each component. And I'll also discuss some results of CAM4 in the couple model, ocean resolutions of 1 degree and atmosphere resolutions of 1 degree and 1/2 degree. So I'm going to give an overview here and not go into too much detail, and I'll start by discussing the effects of changing atmosphere resolution. And something that we've done a lot of work on recently here is how the sea surface temperature is improved in eastern boundary regions when you increase the resolution. This is driven by more realistic coastal winds. The winds are stronger near the coast. Consequently, there's a much better wind stress curl. And basically the problem with the low resolution models is a wind stress curl which is too broad and too strong. It gives rise to a lot of problems. There's also improvements to coastal low-level cloud. This is particularly off Peru, Chile, where resolution of the Andes is important in the high resolution. At the higher atmosphere resolution, you get more equatorward coastal flow in the ocean, which is a cooling advection tendency, as well as more coastal upwelling. But one subtle point which we worked on as well is, in general, the upwelling and flow is still weak at these higher atmosphere resolutions if you have a 1 degree ocean model. And to get the really strong upwelling that we believe is observed requires an eddy resolving ocean model. But there's some subtle details to that I'll mention later. Also want to point out something I'm certainly not an expert on, but the general feeling from CSM, I think, in terms of the tropical cyclones, they're not permitted at 1 degree. They are permitted at 1/2 degree and 1/4 degree resolutions. But the spatial distribution of the tracks is very dependent on model SST bias and large-scale flow bias. An example of that is in the North Atlantic, we have a deficit of tropical cyclones in CSM, certainly in the simulations I'm discussing here, and it's related to a cold SST bias in the couple model, as well as aspects of the large-scale flow in the atmosphere. The intensity distribution is still very dependent on physics and changes to the physics. And another important point is we're going down the line of investigating mesh refinement with the CAM spectral element, work by Collins, Arzik, et al., to refine the resolution over the tropical cyclone regions to improve the solution there. So I'll just give an example of the case for the eastern boundaries and how they're affected by model resolution. So on the top panels of this figure are the SST bias relative to observations of two versions of the CSM, on the left using CAM4, on the right using CAM5. And I just want to focus on the circled regions, which are the warm SST biases in the upwelling zones. As you can see here, present in both versions of the model. I believe they'll still be present to some extent in the newest version of the model, because it is a resolution problem to a lot of the degree. And then the bottom panel shows the improvement with resolution, and the sign convention here is that the same colors, bottom and top, mean an improvement of resolution. And you can see, for example, with the CAM4, you improve the Peru-Chile upwelling quite a lot, a bit less so in the California region, and a bit less so in the Benguela. And again, when you move to CAM5, it's a similar story. It turns out the Benguela is the most complicated region to get right. It involves certainly high resolution in the ocean to resolve the frontal zones and the ocean mesoscale flow. So moving gear now to the ocean resolution. What are the benefits of improving ocean resolution to eddy resolving? So one of the well-known benefits, and it was mentioned in relationship to the rainfall by Jim Kinter, is improvement to SST in the western boundary regions. Due to better representation of mesoscale processes, resolving the bathymetry better, and the deep western boundary currents. And as Jim alluded to, this leads to better location of the surface storm track in terms of precipitation and the low-level winds. They tend to be almost anchored to the warm SST of the Gulf Stream. There's also effects of increasing ocean resolution on the U.S. East Coast coastal sea surface temperature under climate change. It's a paper by Saba and GFDL collaborators point that out. And we have seen similar behavior in high-resolution CSM. So there's some interesting aspects of how, whether this is due to resolving the Gulf Stream better or not, and that's a work in progress. Another aspect, the variability of the sea surface temperature in high ocean resolution runs tends to drive the ocean atmosphere heat fluxes in the mid-latitudes or extratropics. This is something not seen at low resolution, where the SST is mainly driven by the air sea fluxes, so it's going the other way around. And there's, Ben had a paper on this in 2012, and we're following that up with a kind of longer paper looking at observations on that. And just in brief, we see some of the shallow mixed layer biases, which are shown at low resolution ocean in many coupled climate models. They seem to improve with high resolution ocean, and it seems this is kind of early work, so we're looking into it, that frontal and eddy dynamics play a role here, as well as the air-sea coupling of fronts, which is mentioned above. And I'll just show an example from work, and Ben might be familiar from early versions of this with Frank Bryan. This is the correlation between anomalies of sea surface temperature and the latent heat flux, which dominates the heat flux budget for these monthly anomalies. And when you have a positive correlation, it's a sign that the ocean is driving atmosphere heat fluxes. And in the circled regions on this panel, you see, for example, in the OA flux product, positive correlations in the boundary current regions and the Agulhas and the ACC, in addition to the more well-known correlations in the tropics related to things like ENSO and so on. When we go to the high-resolution CSM, we get these patterns, but overall they're a little bit strong. But we see the high correlations in the frontal regions. In the low-resolution model on the bottom right, it's completely absent, almost completely. It's pretty weak. So there's something missing in the low-resolution model. It's responding too much to the atmosphere in terms of the SST anomalies. So I'm probably running a bit short of time. Just briefly say, we also found improved variability of ENSO and NINO 3.4 SST variability when we went to the highest resolutions in ocean and atmosphere. Seems to be a combination of improving both components. And some research on that at the moment is whether it relates to the role of stochastic noise and relates to the stochastic parameterization that Jim mentioned earlier, Tim Palmer and Judith Berner have worked on in disrupting a too regular ENSO in the low resolutions. The caveat here is we only have fairly short runs, about 100 years, and the NINO 3.4 SST variability is also very sensitive to other changes, such as changing parameterizations in the atmosphere. And I think I just want to close with the efforts on the high resolution. And this is the project led by Ben Kertman, and Alicia Karspek and Fred Castruccio provided me the slides on this. We have now a data assimilation capability in CESM, and no doubt Ben will talk about that later. It's being tested out at 1 degree in various papers by Jeff Anderson and Alicia Karspek. And now we're setting up in the 10th degree ocean model, POP, a data assimilation capability to actually assimilate data in from eddies and so on, from satellite data of sea level, as well as in situ data. Obviously, it's very expensive to run this at 0.1 degree, and we've had to replace the traditional ensemble Kalman filter, which involves running a lot of ensembles, which is hugely expensive, with a alternative ensemble optimal interpolation. I don't know the full detail of this, but it doesn't involve huge ensembles. It's an estimate to estimate your ensemble spread, I think. And we have preliminary results from that, which I won't show now. So I think that's all I wanted to say. I hope that kind of showed you a bit more of what's going on with the community of system model and resolution and data assimilation. Thank you.
Justin, that's great. Thank you so much. A very interesting talk. So again, for those logged on online to ask a question, go to the chat option and send me a question directly, or just say you have a question. I can unmute your line. Let me see if anything coming in. I'll wait for a few more seconds and see if we get anything through the chat box. Any questions for Justin? That was a really nice follow-on for Jim's talk, and I think also a good primer for Ben's talk later on. So that was really great. Thank you, Justin. We have a poll question coming up later as well, which I think you've probably primed quite a bit for the responses to that, if people were listening.
Thank you, Dan.
Okay, so I haven't seen anything come in. Oh, wait, we do have one question. So here, let me unmute the line. We actually have a couple questions. Okay, so Justin, bear with me for a sec. I'm going to unmute these lines, and then we can ask. Okay. So the first question is from Zhuo Wang. Zhuo, are you on the line? Zhuo, are you there?
Yes, I'm here, yeah.
Oh, hi, do you want to go ahead and ask your question?
Yeah, my question is, observational data are also a limiting factor for ocean data assimilation?
Well, I think it is. Yeah, I'm not really the person to ask on this. I'm not a data assimilation expert. I think the limiting factor for the high resolution ocean was having to run an ensemble of high resolution ocean models. So that's been sidestepped by using this alternative optimal interpolation method. the data assimilation technique is not so much the step for the data assimilation, not so much expensive, but it is more the ensembles. I think I can't really comment on the limitations of the data at the moment.
Okay, thank you.
Okay, thanks for the question, Joao. And there's one more question, Justin, from someone who doesn't seem to be logged onto the phone. So the question is just to elaborate a little bit on the computational requirements for some of these experiments that you've run. If you can maybe, I guess, speak generally about, the differences between jumping up to 10th degree versus, the atmospheric jumps.
Yeah, a little bit. For our highest resolution ocean and atmosphere, it was something like 250,000 core hours per simulated year. Now, the atmosphere is actually quite expensive, even though it's only 1/4 degree compared to ocean 10th degree. I think with the atmosphere alone, it might be something like 200,000 cores per simulated year. And one of the reasons was when we moved to CAM5 here, we switched on kind of fully interactive aerosols, which was a much more expensive model. Everything got more expensive when we went to CAM4, and partly because of that, switched to interactive aerosols. And I'm not quite sure what's going to happen with CAM6 and the new version. Maybe it'll be a bit cheaper, but that gives you an idea. A lot of the expense was for the atmosphere.
Okay, great. Thank you so much, Justin. That was great, and thanks for the questions. So our next speaker is Eric Swenson. Eric, are you on the line?
Yeah, I'm here.
Okay, great. And I've passed control over to your computer, so if you can go to the Quick Start tab. Oh, great. And I want to apologize also for spelling your name incorrectly on the announcement. It's Eric with a K, not Eric with a C.
That's all right. It happens a lot.
All right. Whenever you're ready, it looks great, so go ahead.
Great. So I was going to talk about some work today, actually looking at the Minerva results that I think Jim touched on. I'm looking at Rossby wave breaking, transient eddy forcing, specifically during the development of different circulation regimes over the Atlantic and Europe. This is work done with David Strauss, part of a DOE grant with Gang Chen and Jian Liu and Ruby Lung. So just to introduce a little, Rossby wave breaking, if you look at, for instance, potential vorticity fields, it should be kind of obvious, just kind of reversal in the typical north-south gradient in PV. So you'll see this overturning feature, the wave breaking kind of near the tropopause tends to occur. And it's presumably crucial in reorganizing like the storm tracks or transient eddies. So they carry out a lot of momentum and heat fluxes that act to either trigger or reinforce or even work against changes in the large-scale circulation. So I'll talk about actually circulation regimes. And the roles of wave breaking, both signs, the cyclonic and anticyclonic wave breaking, I think in the literature haven't been fully quantified in terms of both momentum and heat fluxes, the full three-dimensional eddy forcing, and also just looking at what's going on during actual wave breaking events. Usually it's kind of assumed, people look at changes in frequency and it's kind of inferred that it's related to wave breaking. It's not really clear. Actually, it's not really clear for my study either, but try to get it a little closer. So we estimate the roles of wave breaking during the development of different circulation regimes or the Euro-Atlantic region. And we also see how well this is simulated in seasonal reforecasts or hindcasts. And one of the main motivations was, whether or not horizontal resolution is important. But it turned out we didn't get a very interesting result from that, which I'll touch on. So the model data that I'll show, actually more observational results, but the model data we looked at was the ECMWF model from the Minerva project, the IFS coupled to the NEMO ocean model. So the ocean model is fixed 1 degree and a little finer on the equator. And these, we have 3 different resolutions ranging from 62 kilometers down to 16 kilometers. And that's T319 to T1279. Just run every winter over 31 years, and we have a sample size of 15 members, so it's a good large data set to look at this sort of thing. And I'll look at ERA interim, sort of an observationally based analysis. So to actually identify wave breaking is occurring, we basically look at potential vorticity on isentropic surfaces. And there are other ways you can do this that may even be more suitable, but I looked at the 330 Kelvin, 315 Kelvin surface, and the algorithm I used is similar to that was used by Strong and Magnus-Daughter. I have some additional constraints, like, for instance, the PV gradient and also the size of the breaks. And so here you can see this is the potential vorticity kind of event composites, so you can really see the the breaking feature. We have cyclonic break and acyclonic. So the actual breaking that's identified is indicated by these colored areas. So I looked at kind of the low PV intruding into the high background PV air. So you can get a range of events that have different sizes, and look at just where they occur, which is important for my next point. How do you actually attribute or associate variability with the break? So given a breaking event, it has a centroid position, where it's identified. So I basically look at what's happening around it. So if you have a circle with a radius, so that the area is equivalent to the size of the break, I basically look at the circle is 4 times the equivalent radius around it. So basically it's proportional to the size of the break. I'm just looking around the break. So I consider variability within that vicinity of the break to be related to it. So here we have some event composites. This is all events identified in ERA interim, cyclonic events on the left and acyclonic on the right. You can see the PV features. And then on the bottom I plotted in shading is the zonal wind tendency, and then in contours is the local EP flux divergence. So we infer this as the impact of transient eddies. We just look at the 2 to 10 day variations in winds and temperature. What you see right away is cyclonic wave breaking is associated with easterlies, which is reinforced by the eddies. You can see with the blue color, it's kind of in phase with the dash contours. So, and anticyclonic wave breaking tends to be associated with like a polar jet shift. You can see with the dipole zonal wind tendency. And the westerly component seems to be reinforced by transient eddies. So this local EP flux divergence, it's an approximation done by Trenberth, this 86 paper. It's quite a long time ago, but It's quite useful for diagnosing the role of eddies. You can decompose it into a horizontal component and a vertical component. The horizontal component, people often look at, that's just the momentum fluxes. The vertical component can be quite important. That is dominated by the vertical gradient in the radial heat flux, which we found to be more important than we would otherwise have assumed. And this, we're neglecting low-frequency terms, diabatic heating and friction, so that's the important thing to keep in mind. So just going to the actual frequency, this might be a more interesting result if you care about resolution. Frequency of cyclonic and anticyclonic wave breaking over the Atlantic. So we have area interim results on the left, and the Minerva results from high to low resolution. Alongside that, the cyclonic wave breaking counts on the top, anticyclonic wave breaking on the bottom. What you see are these features, of maximum wave breaking frequency during the winter are very well simulated at all the resolutions we looked at. And if anything, increasing resolution beyond 60 kilometers doesn't really improve how much wave breaking you have. If anything, it might be degraded a little, which was a surprising result. So we kind of hypothesized that if there's any threshold or like dynamical convergence of simulating wave breaking, it already occurs, maybe around 60 kilometers or above, which relates to some previous results, I think, from Athena, where they found an improvement in stuff like blocking, but that we're looking at a range that's at higher resolution than that. We were hoping for an improvement, but we just didn't see it. So looking at also circulation regimes, here I only show results for area interim and Minerva T1279. Basically use a cluster analysis with 500 millibar height. They're quite robust, getting 4 distinct patterns that circulation tends to cluster around. So we have a Scandinavian blocking, Atlantic ridge, then both phases of the NAO. And this is actually highly reproducible in all the Minerva reforecasts. So I didn't really see much sensitivity. And even the actual frequency at which the circulation is designated in each regime didn't seem to be improved with resolution. So I'm just going to show some results for the positive phase of NAO. So here I plotted zonal wind contoured as the total and shading as the anomaly. So during the NAO plus, you get a clear jet extension. And these are observational results I'll show first. And you see a strong reduction in cyclonic wave breaking. This is the cyclonic wave breaking frequency plotted. Anticyclonic wave breaking, you see a bit of an equatorward shift and a slight increase. And if we look at just the developmental phase, so when the pattern correlation is increasing with this NAO plus pattern I showed previously, here I plotted the zonal wind tendency and shading and the EP flux divergence and contours. And you really see that here I partitioned, according to what's independent of wave breaking, what's related to cyclonic wave breaking, what's related to anticyclonic wave breaking. You really see that it's dominated by anticyclonic wave breaking during the development of positive NAO. And that is, the extension of the jet is reinforced by the eddies when anticyclonic wave breaking is occurring. So here, if we look at some vertical averages in the zonal, in the Eastern Atlantic and Western Europe. Here I've plotted again, shading is the zonal wind tendency. We have the climatology on the left and the NAO plus on the right. And again, you see that anticyclonic wave breaking kind of dominates in the Eastern Atlantic. But if we look at the heat fluxes, there's a secondary maximum here in purple. Pardon the abstract art here, that this is actually meaningful. I think I plotted too many things. But the secondary heat flux maximum, which is actually cold air moving equatorward, tends to drive this jet extension just as much as the momentum fluxes. So that was kind of a surprising result. And that tends to just climatologically, it's also important. But when you have such changes in anticyclonic wave breaking, it's particularly important during the NAO+. If we look at the model results in Minerva T1279, you reproduce these features quite well. And that's also true at the other resolutions. That's why I'm not showing the results. But if you want to be picky, you actually see that the role of wave breaking seems to be underestimated a little, and that can be traced to the amount of basically the storm tracks. You know, the transient eddy activity seems to be weaker in the model. So you see these weaker momentum fluxes and the upper level heat fluxes during wave breaking. And that actually is consistent with weaker zonal wind anomalies as well. So that looks like I've run out of time, but there are some further interesting results, especially with blocking, that it's been accepted to JAZ just a couple weeks ago, and that is the paper that's the same title as this talk. So I can encourage you to look into that as soon as it is online. But yeah, thank you.
Great, thanks so much, Eric. Very interesting. So we're going to open up for questions. Again, if you have a question for Eric, just send me a chat message and let me know that you have a question. So I see we already have one in. So Ivanka, I'm going to unmute your line. Give me one moment. Okay, Ivanka, are you there?
Yes.
Okay, Ivanka, go ahead and ask your question. Yeah.
So my question is about the model resolution and the frequency of the wave breaking. And the comparison that was shown there was to ERA interim analysis. I guess the point that was made is that the best representation is at the coarser resolution, which is T319. And the ERA interim itself is at T255. So it's even coarser than any of these models. So how much are your evaluations impacted by the resolution of ERA interim? And do you have independent ways of verifying the frequency that is not dependent on the frequency of the analysis, on the resolution of the analysis?
Yeah, that's a good point. I've only looked at ERA interim, and we are talking about pretty small differences when I'm talking about that difference between model resolution. But I think it is robust. I think it can be reproduced if you only looked at a few individual ensemble members rather than all 15. But yeah, I wouldn't put a lot on that result. I think that the main point is that it doesn't seem to be improved, the actual magnitude of wave breaking with resolution. But I was really careful to make sure that this isn't affected by, any details of the algorithm. I tried to do a fair computation in terms of the amount of wave breaking for each model. So this result isn't so sensitive, and it's also involving only daily data, not like higher, 6-hourly or something like that. So, and those details actually, whether you're looking at sub-daily data or daily mean data or daily snapshot data, even that is results can be sensitive to that. So I don't know if that really answers your question or raises more questions.
I guess the main point is, do we have an independent estimate of what it should look like?
No, I don't. Yeah, I've only compared with area interim.
Thanks.
Okay, thanks for the question, Ivanka. So, Eric, I haven't seen any other questions, so thanks for the talk. Really appreciate it. And we're going to do the second poll at this point. So get the poll ready. Okay, I'm going to open the poll right now. And so this question is, what atmospheric resolution threshold increase will give the greatest boost to the skill of subseasonal to seasonal predictions from global coupled models? And there are 6 options. So what this question is asking is the jump and whether which jump will provide the largest increase in skill. And so, jumping from 100 to 50 kilometers, that's the first option, then 50 to 25, et cetera, et cetera. And there is an option at the bottom to say that resolution is not the answer. So go ahead and take the poll, and I'll keep it open for maybe another minute or so. Again, we're going to talk about the results of these polls at the end of the webinar, so after Ben's talk. And I see that people are jumping in and taking it and submitting the poll, so that's submitting their response, so that's great. In the meantime, I'm going to try switching control over to our next speaker. So our next speaker is Francisco Douglas Reyes. Paco, are you on the line?
Yeah, I'm here.
Hi, Paco. So I just passed it over. Looks good. Yeah, you want to just bring it up full screen, and then just give me another maybe 30 seconds or so with the poll. There's still some individuals taking it, waiting to fill it out. So please, if you haven't started the poll yet, jump in and give it a shot. Okay, so it looks like there's no one still taking it at the moment, so I'm going to close it. You have another 15 seconds if you're still working on your response. Try to finish that up and send it in. And Paco, whenever you're ready, you can go ahead.
Okay, thanks a lot. Thanks for the opportunity to talk here. I think it's great that NAO is organizing these webinars, and I know that from Europe this time there's a lot of interest in following what's being said by the other speakers. What I'm going to give here is a small European perspective of some of the things that have been going on here and that will be going on also in the next few years. I'll focus initially on SPECS project, which is it's a European project that started in 2012 and just finished this year. Here you have a diagram that is summarizing the project, and it's a very complex and large project. I think it was funded at the height of 9 million euros by the European Commission, and the main goal was to produce quasi-operational and actionable local climate information with new European climate focus systems. So basically, one of the main goal of the project was to close the gap or narrow the gap between basic modeling for climate prediction and on one side, and on the other side, climate services. And you can see lots of words that might sound familiar to you there, and basically the one I'm going to focus on today is, well, it's indicated by this arrow here, and that is also linked to a plot from the Betoffice Decadal prediction system, the Process 3, in which they have found out that there is a skill for predicting the NAO, not just in the first winter, but also in the second winter of the predictions. Lots of different focus systems participated in this exercise. Many of them were contributing to the increased resolution climate prediction experiments that were all coordinated. And among them, I'll show results here from the unified model from the Metoffice, and also ECEarth, which is the European community model that has been run by my institution, the Barcelona Supercomputing Center, KNMI, SMHI, and the NAO. Before jumping into some specific material illustrating what we've been doing with the use or the assessment of the impact of resolution increase in climate prediction, I want to add that the main motto of this project, and also other European projects these days, is that climate data is not climate information, and that most of the time we are generating climate data, maybe also some diagnosis of what our models and our focus systems are doing, but that's not automatic climate information. I'll go into this at the end of the presentation. An illustration of what has been achieved by increasing the resolution of some focus systems. These are results from the Process 3 focus system that the Metoffice uses for their operational decadal forecasts. And what you can see here is an illustration of some gains in skill for the West African precipitation, in particular the Sahel precipitation, at a multi-year time scale. So the top row shows the skill for the 2 to 5 year forecasts over the period 1960 to 2014. And in red, you have the results from the forecasts. This is the ensemble mean scaled to take into account the decrease of the focus variability by performing the ensemble mean. And in black, you have an observational reference taken from GPCC. And this is the first time that the decadal focus system can show this very nice decrease and also increase in stabilization of the precipitation in West Africa, in the Sahel region. There is also, as a reference, a measure of the interannual skill, or the skill of the interannual forecasts. So basically the forecasts from the first year of the decadal prediction. And some of this skill can be attributed to the increase in the resolution that took place in the Metoffice model a couple of years ago, notably by increasing the ocean resolution to 1/4 of a degree in the NEMO model. So other illustrations can be seen from here in this overhead, where some results from the ECEarth 3 focus system are shown, this time for seasonal forecasts of the NEO 3.4 time series. This time we performed 10-member ensemble hindcasts starting on the 1st of May over the period 1993 to 2009 in 3 different experiments. In blue, you have the experiment with the highest resolution possible. In this case, it was 40 kilometers in the atmosphere, so T511, and 1/4 of a degree in the ocean. In black, we have the results for the standard resolution configuration of ECEarth, which is 1 degree in the ocean and around 70 kilometers in the atmosphere, T255. And in red, you have an intermediate resolution that has the standard resolution in the atmosphere and high resolution, so 1/4 of a degree in the ocean. And what we can see is a gradual increase of the correlation on the left. This is the correlation of the ensemble mean over those 17 years. And in solid blue, we see that the high resolution configuration is the one that gives the highest correlation. We can also see, by comparing the solid blue and the dashed blue, the impact of verifying our forecasts with a different observational reference, in this case ERSST instead of the European Space Agency Climate Change Initiative CSIS temperature. And I'll go a bit later again into this issue of the importance of the observational reference uncertainty. The main message here is that there is a gradual increase as we start increasing the resolution of the different components of the system. Unfortunately, we don't have the fourth experiment in which we keep the standard resolution in the ocean and we increase the atmospheric resolution. But we plan to repeat these experiments in the future with the CMIP6 version of ECEarth. So there are some aspects that are improved by increasing the resolution, and some of these improvements can be traced back to a decrease of the biases in the forecasts. So in the top row, we see the biases of the standard resolution configuration of ECEarth on the left, and as we move to the right, we can see the differences in the systematic error for the 1 month lead seasonal averages for boreal summer. Again, the improvements are gradual, but unfortunately they are not as strong as we expected. There is an improvement in the western boundary currents, also in the equatorial Pacific and Atlantic, but it's only by looking at the precipitation and the corresponding winds that we can see a large improvement by increasing the resolution. However, none of these improvements are astonishing, or they are really the panacea, as Jim was saying during his presentation. In SPECS, we performed plenty of sensitivity experiments to the initialization of the CIs, the initialization of the land surface, both the snow and the soil moisture. We are trying to find out and illustrate which are the most relevant aspects in which the community, in particular the operational systems, should focus when they are trying to increase the forecast skill in their systems, and in particular focusing on land areas, because that's where most of the users and the climate services have an interest. In one of the exercises, we tested the impact of initializing the land surface, and I think along the lines of what was done in Glacier 2, although this time instead of what was done in Glacier 2, in which the high gusts were performed up to 2 months of forecast, this time in SPECS, the experiments were performed all the way to 4 focus months, which is more relevant to the seasonal focus timescale. And what you can see here is an illustration of the impact of correctly initializing the land surface taken from the high gusts for the summer of 2010, in particular over Europe. This is the year in which there was a heat wave over Western Russia, and what we can see is the impact of that heat wave in Interim. This is the seasonal mean of temperature to meet the temperature in the region, and we see that there is a very strong positive anomaly of temperature in the area. When we initialize the forecasts by taking climatological soil moisture initial condition, we can't find a definite probability of having high temperatures over that summer. Instead, when the soil moisture is correctly initialized and taken from Ireland, we see that the probability of which is what is shown on the right plot for having a strong temperature anomaly in Western Russia and Central Europe it appears. So somehow the main message of this exercise, and this is only one illustration from one model, 4 other models contributed to this multi-model sensitivity experiment, is that initializing the land surface is more important than what it was thought at the beginning a few years ago, when, for instance, in Glacé 2, the signal from the initial conditions tended to disappear after a few weeks. I mentioned these results because one of the questions that was raised during specs is whether these results, whether the importance of the initializing of specific components are robust when we increase the resolution. So what we did was we rerun the experiments and performed the same experiment with a different version of ECRF. In this case, it was ECRF 3. Again, we initialized a set of handcasts at high resolution. In this case, it was the configuration of T511 Olga quarter, so around 40 kilometers in the atmosphere and a quarter of a degree in the ocean. On the left, initial conditions taken from Ireland, and on the right, you can see the difference in terms of the correlation of the ensemble mean. There are 2 main messages from these results. The first one is that the initialization of the land surface, the correct initialization of the land surface with the best initial conditions that we can generate, really plays a role even when we increase the resolution. So the message is robust. And this message is robust as well when we use a different version of ECRF. In the previous overhead, I was showing results from ECRF 2.3, which was our CMIP 5 version. ECRF 3 it's an intermediate version between CMIP 5 and CMIP 6. The second message from this overhead is that the difference appears in regions where that have been already demonstrated to be very sensitive to the to soil moisture in summer. And the other message is that usually it's quite hard to detect differences that are statistically significant when we are comparing 2 experiments that are only different in a small thing, in one aspect, like in this case, for instance, the initialization of the land surface. Usually, we don't pay that much attention to the power of the statistical tests that we are using when evaluating the impact of any changes in our systems. And the increase in resolution being one change that has a marginal impact in the quality of either the climate simulated by our systems or the focus quality exhibited by the focus systems that we use. We started paying attention to the tests that were being used to assess the differences and the impact of changes that are introduced. In particular, in this case, instead of using the Fisher test for the differences in correlations, we explored the literature, and we found out that the Steiger test, which is a different version for the same inference question, was more robust because it had more power, and also because it took into account the fact that is usually neglected, that the predicted time series from the 2 experiments are correlated among each other. I mentioned the relevance also of the observational uncertainty when I was explaining the differences, the impact of the increase in resolution in the ECR3 handcasts for the NEO 3.4 SST time series. This is an illustration of how relevant the observational uncertainty is when considering the total uncertainty in the skill scores that we usually look at. Most of the time, we are shown results from focus systems that have no uncertainty estimates for those skill scores. And the same applies to the reliability estimates for the forecasts. In this particular case, we can see an illustration of the partition of the total uncertainty depending on the source. In blue, in dark blue, you can have the impact of the record length. In orange, the impact of the ensemble size, and in green, the impact of the observational uncertainty. With such a large total uncertainty, and in particular with such a large uncertainty associated to the observations that are being used for the assessment of the quality of our systems, then what is even more important for the assessment of the impact of specific changes in our systems, we are promoting the idea that the observational uncertainty should be explicitly taken into account when considering the impact of any changes in the models and the forecast systems. Jim mentioned in one of his overheads.
I'm sorry to interrupt, but if you could finish up in the next couple of minutes, that would be great.
Absolutely, yes.
Thank you.
Jim mentioned the impact of what could be done when increasing in 10 times the computational power available to perform experiments. I would say that when you're offered 10 times more computing power to perform your experiments, you should make your effort to convert that into 20 times more power. And this is done by investing much more into making our codes more computationally efficient. And this is just an example of one of the efforts that are being made, not just in my institution, but also in Europe, by, for instance, investing time in reducing the precision of some of the variables in our codes. In this case is for the NeMo 3.6 model. Just to conclude, I would like to mention an exercise, another European project that has started recently, 1 year ago, that is coordinated by Malcolm Roberts and Luigi Vitale, and in which this exercise is to understand the impact and the benefits of increasing resolution both in the ocean and the atmosphere is going to take place in a coordinated multimodal fashion. And here you have a list of the different models participating in this project, which is called Primavera, and that is in quite an ambitious way going to try to, on one side, contribute to HARSMIP, but on the other side, to try to nail down what are the processes that are effectively affected by the increases in resolution. And I think I'll leave it there. Thank you.
Paco, that's great. Thank you. Just while the slide's up, I was wondering, what does FCM mean in the left column of that table?
Sorry, FCM?
Yeah.
Where do you have it?
Oceanic resolution, comma, FCM, and atmospheric resolution, comma, FCM.
Oh, it's the frontier simulation. So we have two types of simulations. The standard contribution to HARSMIP, which for most of these systems will be of around 25 kilometers for the ocean and the atmosphere. And then we have a set of frontier simulations in which some of the systems will contribute to long coupled simulations with around 10 kilometer resolution, both in the ocean and the atmosphere. Of course, taking into account that each system is very different, but the experimental setup is shared among the different models. Okay, that's great. Thank you, Paco. And Paco, I also wanted to thank you for being on this late in your day. I know it's a little bit after 5 at this point for you, so thanks for calling in your early evening. We appreciate that. We have time for perhaps one quick question for Paco. If anyone would like to submit a question via the chat feature, please go ahead and do that. I'll wait maybe about 10 seconds, see how fast people can type. You can just tell me you have a question. If you have a question, you don't have to type out the whole question. Okay, I haven't seen anything come in yet. So, Paco, thank you so much for the presentation. Very interesting. Yeah, my pleasure.
Okay, I just passed control over to Lucas. Lucas, are you on the line?
And I'm in share right now.
Hey, Lucas, are you there?
Yes, I am.
Oh, okay, great.
Okay, and I should be sharing it now, am I correct?
Yeah, I can see it. If you can just go full screen, that would be great.
Awesome, okay.
Perfect. Okay, go ahead.
All right, well, thank you, everybody, and good afternoon. I'm going to talk a little bit about what applications are using the FD-Cube dynamical core, both here at GFDL and at other modeling centers, to be able to push towards increasingly high resolution and in particular to convection permitting and convection resolving scales in both weather and climate models. Before I go on, I do want to briefly introduce the GFDL FD-Cube team, the team that's most closely involved with developing the dynamical core, and also helping to integrate it in with other models that are being developed here at GFDL, NCEP, NASA, University of Oklahoma, ESRL, and elsewhere. And I bring this up because I just want to point out this is a very, very team effort. There's been a lot of people who have been involved, particularly S.J. Lin, in the development of this dynamical core, and some of the, and many of, been closely involved in many of the models that have been developed that use FD-Cube and its predecessors. So what exactly is this FD-Cube thing? Well, FD-Cube is the GFDL finite volume cube sphere dynamical core, and this is the quick brochure of some of the high points of the core. I'll just go through this quickly. FD-Cube is fully finite volume in the horizontal, vertical, and in space, or excuse me, in time. Has an excellent advection scheme, has a non-hydrostatic option, runtime switch to do so, and rigorous moist thermodynamics. It's mimetic, which means that it captures recaptures important physical behaviors. It's very adaptable and robust. It adapts very well to a number of different physics and chemistry packages, which is part of the reason why it is so popular. It's used in a very large number of physics schemes all around the world, and it's also renowned for creating models that couple very well with the ocean. FD-Cube is known for being flexible. You can choose an arbitrary vertical level setup, and we're also capable of grid refinement by nesting and or stretching. FD-Cube is engineered from day one to be fast, and the reason for this is that a faster model can help us turn around our development time more quickly and allow us to speed up our model development, get to a better model more quickly. And it's been very well tested, very proven in a number of different environments and a number of different scales. It does excellent at maintaining large-scale circulation. It's been increasingly shown to be very useful at the mesoscale and the cloud scales as well. And as I alluded to earlier, FD-Cube is very popular. It's a global core choice for both NOAA and NASA models. Its earlier version, FD, is standard in the climate models used for CESM and is also used in the geochem community models. And both of them are being considered, both of them are considering using FD-Cube in the future. In fact, geochem has already moved towards using FD-Cube. But FD-Cube is just a dynamical core. It's not a complete model. And in particular, to get a complete model, you need to add in the physics, the land model, and the ocean model. And that's why, and indeed, that's the purpose of the large modeling groups in GFDL, at NCAR, at NCEP, and a number of different laboratories that use FD-Cube-based models, is that there's still a lot more work that needs to be done to make a complete model. Here's a variety of different applications that FD-Cube are used for, from a couple long-term coupled climate integration and atmosphere climate simulations. Here's examples of the upper troposphere temperature trends and tropical cyclone trends, seasonal forecasts and medium-range forecasts, particularly for tropical cyclones, which has also been used more for more general purpose seasonal, subseasonal forecasting, orographic precipitation, and a couple of cloud-scale applications, as well as the famous NASA video that shows the excellent advective qualities in an aerosol simulation. So I want to discuss a little bit about some of the zooming capabilities in FD-Cube, and you can certainly, and I'll discuss a little bit about globally uniform high-resolution simulations a little bit later, but in the meantime, and both during this presentation and in the meantime when computers can catch up to doing that regularly, we can use grid refinement to zoom in on features of interest. And there's two ways of doing that in FD-Cube. One is to use grid stretching, the other is to use grid nesting, which I'll describe here. Two-way grid nesting, which in this case is very similar to what's been used in regional weather models, but since been advanced to be more compliant with the FD-Cube discretization, has a number of different advantages. In particular, you can run the nested and coarse regions simultaneously to get consistent global and regional solutions, and without having to first run your global model and then run your regional model after that. Grid nesting also has nice flexibilities to it. In particular, you can choose the correct time steps and the correct physics for both grids. You can use a long, more efficient time step for the coarse grid, and you can choose your physics that are appropriate for those scales. And in particular, you don't need to choose a compromise between your high and low resolution regions, and you don't need to have a particularly sensitive scale-aware scheme for this purpose either. And grid nesting is also flexible. You can put nests where you want. You can put nests within nests, and you can also nest combined with grid stretching, something that we've used here at GFDL to achieve efficiently very high resolutions over a small region. So I'm going to describe two of the models in two applications of global to regional nested FV cubed. The first one is by some runs that my postdoc Kun Gao is doing, and he's looking at seasonal predictions using the GFDL HIRAM climate model. So HIRAM, that's a GFDL atmosphere climate model. It uses the AM2 physics and the non-hydrostatic FV cubed, with some things introduced from the more recent AM4 physics, in particular the UW GFDL double plume convection scheme, and GFDL 6-category microphysics that we've developed to be able, that's more appropriate for high resolution simulations. In particular, the scheme contains 6 categories, including 3 categories of prognostic precipitation: graupel, snow, and rain, which is more advanced than many than the typical global schemes that are used in earlier versions of the GFDL models or at NCEP. We're following the methodology of the very successful seasonal predictions by Jianhui Chen and S.J. Lin using HIRAM as well, in which we do seasonal forecasts by freezing the SST anomalies and allow them to write on top of a time-varying climatology. In this case, we've extended to the subseasonal forecasting, in which at the beginning of each month during hurricane season, we take a 5-member perturbed physics ensemble. We perturb the parameters in the convection scheme, and we do 5 runs, each a 30-day length, and then that's what we use for verification. In this case, we're showing results from 2 different modeling systems. One is to use a uniform 25-kilometer grid, the same as Chen and Lin, and the other one is to use an 8-kilometer two-way nested grid inserted over the tropical Atlantic. So here's some results. Here we're showing results for just major hurricanes, category 3, 4, and 5 hurricanes. And we know that simulation and forecast of major hurricanes is greatly improved by going to increasingly high resolution. And you can see that going from the 25 kilometers to the 8 kilometers in the top row doubles the number of major hurricanes per forecast period. So we're very close to the observed number of major hurricanes. And plus, the forecast quality is improved by a good amount. You can see that we're now getting a better correlation between the observations and the model count of major hurricanes by going to the nested grid. Now, when you can also take a look at accumulated cyclone energy, or ACE, and indeed it's the major hurricanes that cause the most damage, since they have, partially due to the fact that they have the most kinetic energy in the winds. And you can see that we get, again, a doubling of the amount of kinetic energy in our simulation, in our seasonal predictions, as well as getting, again, an increase in the correlation between the between the observations and the forecast. We get an increase in subseasonal forecast skill by going to 8 kilometers. Another model that we developed at GFDL is what we call FVGFS. This is originally developed for 13-kilometer applications during NGGPS, and then since extended to be able to be appropriate for convection resolving forecasts down to 3 or even 2 kilometers. FVGFS is the non-hydrostatic FV cubed coupled to the GFS physics, with the GFS physics replaced by a GFDL 6-category scheme. And this is a prototype and proof of concept. It's not intended to be the next version of GFS, not hardly at all, but this is simply something that shows that what's capable with an FV cubed powered model and more advanced physics. So this can not only show that what you could do with the new next generation GFS, but also the potential for a unified global to regional forecast system. So I'm going to show 2 configurations here. One is a nested grid over the continental United States down to 3 kilometers that's useful for severe storms forecasts, as well as some hurricane forecasts, like the forecast of Hurricane Patricia from 2015 shown here. I'm also going to show results from my postdoc, Andy Hazelton. He's put a nested grid down to 2 kilometers over the North Atlantic, which has been useful for forecasts of intense hurricanes. So here's one example here. This is the 2013 Moore tornado outbreak. This is initialized 72 hours in advance. Here we've turned off the GFS deep convection scheme, which I found does, this convection scheme seems to cause problems with continental deep convection. So I have turned it off, which greatly improves our results. And we're also using the 6-category GFDL microphysics here, which also helps improve the results quite a bit. So if you compare the simulated radar image against the observed radars, you can see some differences. Our reflectivities are a little on the high side. Right? The storms are a little bit shifted into the south, but other than that, you can see that the large-scale squall line is in the correct place. You can see the individual supercell thunderstorms, as well as some smaller-scale details as well. The smaller-scale details are best seen by the plot in the lower right-hand corner, the updraft helicity, which shows the product of vertical velocity and vertical vorticity, which is treated as a signature of mesocyclones or severe thunderstorms that are often associated with tornadoes. And if you do look closely at that, you can see the individual grid scale signatures of the tracks of the rotating updrafts. I should point out this is an hourly mean quantity, which allows us to see not just instantaneous values, but also, hourly maximum value. So you can see the full tracks over the course of 1 hour of the simulation. So indeed, we are picking up the individual rotating cells with very high fidelity in this case. Here's another example forecast. This is the 2012 derecho that went from Chicago to Washington, D.C. This has been initialized 72 hours in advance, and previously it was believed that the predictability for this event was about 12 hours. And here's a 72-hour forecast, and certainly it's not, there are some things, again, that differ from the observations. We're about 4 hours early in creating our derecho, and it's a little bit farther to the south than was observed. But you can see many important features in the derecho itself. You can see the large trailing stratiform region. You can see the individual convective cells at the leading edge, and you can see in the lower right-hand panel, you can see the vertical velocity, a very well-defined set of updrafts at the leading edge of the cold pool in front of the derecho, and the intense winds right behind it. So this is a good example of what is possible with an FDQ-based system in FDGFS. So now I'm going to show a forecast of intense hurricanes, in this case Hurricane Matthew. This is done by my postdoc Andy Hazelton with the verification done by Morris Bender. You can see here that we show two different forms of FDQ here. The one in red is our standard form with the microphysics we've been using. This is again a 2-kilometer run, nesting a very high resolution meshing the H-warp, and with our GFDL microphysics, just two different variants of the microphysics. And we can see that the line in red, the standard microphysics I showed in the previous slide, does get a very good result. Even though it's initialized from the 13-kilometer GFS initial conditions, it very quickly equilibrates and then produces a strong hurricane, matching the observations and the much better initialized H-warp simulation, the H-warp forecast, as well as being able to represent the intensity a little bit late with the intensity drop at about between 72 and 84 hours. But we are able to start picking up the full intensity and some of the decay phase of the storm. You can also notice in the right-hand column, the top is observed radar, the bottom is the simulated reflectivity at about the same time. And you can see many fine-scale structures in Hurricane Matthew in the eye wall and the rain bands and individual convective cells. Finally, I want to briefly discuss some of the efforts that are being done at GFDL and at NASA for global convection resolving forecasts. Something that has been done actually for 10 years now. At NASA, they've been doing a global 3.5-kilometer forecast since 2009. Here's one animation of such an experimental forecast. And both us and NASA Goddard have been working to improve their modeling systems to make these sort of simulations even better and taking advantage of even larger computational facilities to be able to push these things out faster. What you're seeing in the bottom panel is a 10-day forecast of from 3-kilometer FDGFS. And you can see two things here. One is that NASA has, unfortunately, a higher production budget than we do. But also that we have we're able to do this very nice forecast, which turns out to, in some cases, be have a better skill even than the operational European Center forecasts, as well as being able to pick up a lot of the finer scale details that coarser resolution runs won't get. But also, this is since FDQ and the models created from it tend to be very efficient, that we can get these runs done fairly quickly. Right now, we can get, with 18,000 processors on Gaia, we can produce a forecast in 45 minutes, which is less than 5 times or about 5 times the operational requirement, which says that there's a possibility of being able to do operational 3-kilometer forecasts within the near future. But you need to have a model that has a dynamical core with it that is both efficient, so you can run these things in a reasonable time, and is good at simulating the small-scale features through its non-hydrostatic dynamics and better advection schemes, something that FDQ both should have. So I'm going to leave this up here, but I'll briefly wrap up. I want to touch on two major points. One is that we are working on a 3-kilometer real-time system for the hazardous weather testbed spring experiment that we're going to be going to here in a few months. So we're all very excited about participating in that. In the longer term, we're still going to be working with different laboratories and the different agencies and the university community to help bring in new physics schemes and also improve the initialization and to help improve these models further. And of course, we're working with existing groups that are developing, the HWRF group, the NCEP NAM group, and of course the groups here at GFDL developing the climate models to be able to use these technologies to push towards ever higher resolutions, to do regional climate simulations, seasonal forecasting, and so on. So thank you, and I'll take any questions.
Okay, Lucas, that's great. Thank you so much. So if there are any questions for Lucas, please send a chat message to me again. Just let me know you have a question, and I can unmute your line. Okay, so I skipped one of the poll questions during the last talk just to save some time, but I do want to do this final poll question. So this question, it's a nice preface to Ben's talk. It also follows up a little bit on Justin's discussion and Jim's discussion. So I'm going to open the poll now. And the question is, to improve the seasonal prediction skill of global coupled models, it is more important to focus on increasing atmospheric resolution than oceanic resolution. So again, please choose your answer and submit, and we'll talk about the responses to this and the other 3 poll questions at the end of the webinar after Ben speaks. So I'm going to go back and see if anyone has submitted a question by the chat feature. Okay. Lucas, I haven't gotten any questions yet, so I think I'm going to move along to Ben, but if something comes up, I'll throw it back to you. Thank you so much for the presentation.
Well, thank you so much.
Hey, Ben, are you on the line?
I'm here.
Okay, great. I just passed the presentation privileges over to you, so just go to the Quick Start tab and then share your screen.
Can you see it?
No, not yet. Did you click the share screen button?
Let's see what's going on here. Hold on. How about that?
It's loading. It seems promising. Okay, yeah. Looks like we're in business.
Okay.
And then let me just close the poll.
So, can you see that?
Yeah, it looks good. Let me just see. It's a little small on my side. I think it might be, yep, okay. I was able to adjust it. Let me just close the poll. So I'm just going to give folks 20 seconds. I'm going to close the poll now. If you are thinking of responding, please do it now. And there are, let's see. It looks like, okay, the poll's closed. Okay, Ben, so whenever you're ready, please go ahead.
Sure. So I appreciate everybody staying on the call for the last talk, and I appreciate the invitation to talk here. And I also want to thank all my collaborators, my research scientist I'm working with at University of Miami, Leo Siquiera, and then many collaborators at NCAR, far too many to list, and Justin listed some of them, but there's many others too. And of course, GNU and COLA folks through the PETA-APPS project, but also more recently, Boa Huang and Christina Stan and Jim Kent are also collaborating on these efforts. So the one piece of motivation I want to start out with is this is actually from results from the NMME project, and this is the rank probability skill score for forecasts on the top initialized in January, and it's a JFM mean. This is the rank probability skill score, and then this is June initial conditions verifying in JJA. So these are relatively short forecasts, one season lead or a half season lead, whatever you want to call it. And red areas are good skill, and blue areas are consistently bad skill, so negative skill. And what I wanted to point out here is that a lot of these blue regions are eddy-rich regions in the ocean. So what's interesting is that you're using a model that doesn't actually resolve ocean eddies, and that's producing skill scores that are decidedly wrong, systematically of the wrong sign. So you're doing something really quite fundamental if if everything were, we just had bad skill there, or no skill, we would expect 0, but these are systematically negative. So it tells us that resolving ocean eddies may it's a hypothesis, may play an important role in the seasonal forecast. So what I want to talk about, of course, are some experiments we've been doing with CCSM4 and additional experiments with CSM1, where we're running the atmosphere at a ½ degree, and we're running the ocean 2 different resolutions. One is a 10-kilometer ocean, or a 1/10 of a degree, and the other is this sort of standard NMME resolution, or climate resolution, if you will, that's 1 by 1, telescoping to about a 1/3 degree in the tropics. And so just a quick summary of the results I want to present are some results on decadal predictability that Justin hinted at a little bit, and then I want to talk a little bit about the actual prediction experiments we've done. In this case, I'm going to focus on the subseasonal timescale. And I'm not going to have time, but I can see that now. I just won't have time. But I also want to talk about this. I wanted to talk about this question of who's forcing who. That question of is the atmosphere forcing the ocean, or the ocean forcing the atmosphere, completely changes when you go to this high resolution model. And Justin touched on that a little bit, but we've had additional experiments with the interactive ensemble technique to really highlight that. Just a quick, bit of eye candy. This is the top panel here, is showing you the surface current speeds from a 50-year simulation after 100 years of spin-up runs. So it's a 150-year run. This is the last 50 years. These are showing surface current speeds from what I'm going to loosely call the eddy resolving model, and then the bottom panel is showing you surface current speeds from the typical IPCC class or seasonal prediction class model. And so you can, it's not hard to imagine you're resolving a lot more boundary currents. The Southern Ocean, of course, lights up with a lot more eddy activity. And the deep tropics are fairly similar, except there are some, distinct differences in boundary currents and some features of where tropical instability waves are and things like that. Jim Kinter already showed this picture, so I'm just going to jump forward. So the first result that I want to talk a little bit about is there's decadal variability that's emerging in these simulations, and we've now done about close to 400 years of simulation with this eddy resolving coupled model, and we've started to really dig into the decadal variability. And this slide, what I'm showing you here, is an analysis of sea surface temperature in the North Atlantic. The top panel here that's marked observations, this is based on SODA data. This is an EOF analysis of SST. The second panel is from the high resolution model, similar analysis of SST, and then the bottom panel is the low resolution model. And the point of those 3 panels is to, not that the high resolution model is perfect, but you're getting something that looks similar to observations. The boxes are identifying regions of action and the dominant time scale in those regions. So the time scale is definitely a little bit shorter in the high resolution model and compared to observations, but you can see there's something happening along the Gulf Stream front where that rainfall variability is very different, and that's producing low frequency variability that's basically absent from the climate resolution model. Indeed, the dominant timescale here in the low resolution model is on the order of 3 years and is intimately connected to ENSO and really just not present. And then on the other side of this panel, I'm showing 2 plots. One is just showing you what the heat content looks like with this SST mode, and the black line here is really showing you the SST front, and you see it's sort of a classic pattern. You see in this case, you see positive anomalies here and negative anomalies in sea surface temperature in the North Atlantic, and you see some oscillation between these 2 regions, and it's really related to the SST front and the subpolar and polar gyres. The top panel, this is really a really interesting plot, and going in all the details would take some time, but what this is actually looking at the 200 millibar jet. So the argument here is that this is not just at the surface, this is actually penetrating aloft, is related to convection, and I'm going to show you it has terrestrial responses over both North America and Europe. But what this panel is showing you is that in the black curve is showing you the high resolution model. It's a power spectra of the position the 200 millibar jet. And so what it has is low frequency decadal oscillations in the jet. It's not that it's sitting in one position for 10 years and another position. It just has a lot more low frequency power in its undulations, where you really don't see any preference for that in the low resolution model. And then this panel here is just showing you again that those SST signals from the low resolution model for both the warm and cold cases, which is, you see a very much a surface trapped, very much a surface trapped signal. This is a vertical section along the SST front. You see very much a surface trapped signal in the low resolution model. But in the high resolution model, this is the warm and cold, you see a subsurface signal. So the eddies are really enhancing the vertical communication, not just the variability, but how that tends to work in the model. And so you see pretty much a barotropic response, at least in the upper 800 meters or so. Oops, sorry about that. And then this is the question that I want to get to, the terrestrial response. And so I'm going to start with the bottom panel down here. So this is the 200 millibar heights in the contours, and the SST in the shaded. And this is a blow up of this region over here, and this is the warm case. And so it's showing you that indeed, that SST signal is actually going along with the 200 millibar height signal. So this is the 200 millibar heights that go along with that SST pattern. And then the top panel is showing you the correlation of 2-meter daily minimum temperatures that go along with that pattern. And so you can see there are, pretty robust signals both over North America and Northern Europe that's associated with this pattern. And you can see from the 200 millibar heights why that both North American and Northern European signal would light up. And so I just want to look. One of the other things, and Justin mentioned this, is part of our collaboration on the EASM project is looking at decadal predictability, not just the not just the data assimilation problem. And so we've done a number of idealized decadal predictability runs with this 10-kilometer ocean coupled model. And I just want to show you one case, one 3-member ensemble case of this cold event in the Gulf Stream. And so what this picture is actually showing you on the left-hand side is showing you the PDF for the 2-meter temperatures over Northern Europe. The gray shading is the model's PDF. The blue are the 3-member ensembles, and then of course the red is this particular control case. So you could think of this as a 4-member ensemble if you like, but so this is the model is showing, and this is a lead of years 2 through 6. So you can see that the model is showing you a clear shift in the probability of 2-meter temperatures, and in fact the probability is that 2-meter temperatures are shifting to being quite a bit colder, and that the model thinks, this is an idealized predictability experiment, of course, so the model, that's within the context of the model. So the model thinks this has a significant predictability on decadal, or at least 5-year timescales. So the next thing I wanted to talk about, and I guess I'm already running pretty low on time, is just some actual prediction experiments that we've been doing with this 10th of a degree model. And in this case, these prediction experiments we're taking a relatively speaking, low resolution data assimilation product and shoehorning it into the 10th of a degree model. So we're taking the CFSR, which is sort of a seasonal climate model resolution, and jamming it into this a 10th of a degree model in these prediction experiments. And it's really the baseline, if you will. It's the control set of cases that we're going to compare with the data assimilation that my NCAR colleagues, Alicia Karsbeck and others, are doing at the actual 10th of a degree. So this is sort of a, do you really need to do the data assimilation at a 10th of a degree? And I'm quite sure the answer is yes, but this is just a control set case. And so this is just showing you looking at a particular boundary current region. So the biggest differences we're finding in these experiments is, of course, on these subseasonal timescales, is really in the boundary current regions. And this plot here is just showing you in the colors, the shaded region over the ocean is just showing you the sea surface temperature, and then the arrows are the 850 millibar moisture fluxes vectors. And when you sort of squint your eyes, they look very similar. And so this is looking over fairly short time scales, and they should look similar. And the point I'm trying to make here is that the climate drivers, the large-scale climate drivers on these sort of subseasonal time scales are quite consistent among the low-resolution model and the high-resolution model, as to be expected. And then when you start to look at details, what you can see is along the coast, the temperatures in the high-resolution model are considerably warmer in this case. And that's really the point I want to make here is when you start to look, so now this is the rainfall that goes along with that pattern. And so you can see, yes, on the large scale, there's the dry to the south, the wet to the north. They look fairly similar in the low resolution and the high resolution. But when you actually look along the coast, whoops, sorry about that. When you actually look along the coast, you can see that the high resolution model actually has this tongue of increased rainfall that's associated with the boundary current. And when you look at, this is now a section along that box, this is a vertical section along the box in the ocean, in the atmosphere. The shading in the upper panels is the atmosphere, is the cloud cover. The contours are the vertical velocities. And the bottom two panels are the ocean state, are the ocean current system, ocean subsurface temperatures. And so you can see in the low resolution model, it's really behaving like a mixed layer model. The dynamics are not really playing, or at least, you know, maybe it's just gyre circulations. There's not real eddy activity, not a boundary current. And then in the high resolution model, you can see the boundary current has an effect. You can see that actually is producing sea surface temperatures that are enough to excite enhanced vertical motion, cloud cover, rainfall along the coast that's completely absent in the low resolution model. So now this is a composite of retrospective forecasts. So these are actual, you know, real retrospective forecast cases, and these are difference plots. And this is based on truly subseasonal timescales. So this is, you know, this is the week 3 problem, if you want to be really clear. These are lead times of days 15 through 25. This is a total of 3 different cases. So 1 January 1985, 99, and 2000. And we chose those cases because they were these extreme cold cases of cold temperatures off the coast of South America. And then these plots here are showing you just the differences. And so the top panel is the difference in SST, and so you can see the strong coastal warming. And these are 3-member ensembles, strong coastal warming. And so what's really interesting about this plot is that the differences in SST are large and set up in 15 days. To me, that's really quite impressive that we're getting those differences right away in the forecast mode, and I'm emphasizing that these are initialized with exactly the same initial condition data sets. So that current difference sets up really very quickly. The middle panel is the turbulent heat flux, and then the bottom panel is the cumulative precipitation over that 11-day period. So Dan, do I have any more time, or am I done?
Yeah, Ben, if you could wrap up in a couple minutes, that would be great.
Okay, so just one or just Dan wants me to wrap up in 2 minutes, and so I'll try to touch on this. This is a plot that Justin already talked about. The upper left, if you will, is this ocean forcing atmosphere plot where you look at the correlation of SST and heat fluxes, and you can see a big difference in between the high resolution model and the low resolution model in terms of that local coupling between SST and turbulent heat fluxes. And I just want to point out that when you run this 1/10 of a degree model with the interactive ensemble coupled to 10 atmospheres, and I know a lot of you don't know what the interactive ensemble is, and so I apologize, I'm out of time, but this is just looking at the correlation between the signal and the noise, and you can do that in the interactive ensemble. And what ends up happening is you see a lot stronger correlation between, you know, the SST also forcing coalescence of signals because there's that strong SST forcing that happens in the mid-latitudes that's not present in the low-resolution model, which is the bottom panel. So the top is this high-resolution interactive ensemble, and this is the standard resolution interactive ensemble. And so it's missing a lot of that coupling between the atmosphere and the ocean in the mid-latitudes that happens. And then this is, again, just another demonstration of that. But what this is really saying is that there is a coupled variability that's happening in the high-resolution model that's just completely absent in the low-resolution model. So wherever you see big red and yellow signals happening in the high-resolution plot on the top, and they're absent in the low-resolution model, that's really saying that there's some coupled variability that's happening in the high-resolution model that's absent in the low-resolution model. So my point here is that this is not doing high resolution for high resolution's sake. This is basically, I'm making the argument that these ocean eddies are actually fundamental to subseasonal all the way out to decadal timescales, and it's intimately affecting how the coupled model behaves, and ultimately is a source of predictability that up until very recently we're basically ignoring. And so I'll stop there.
Hey, Ben? Ben, are you there?
Yeah, I'll stop there. Yep.
Okay, great. Thank you. So if there are any questions for Ben, please send them in now via the chat feature. In the meantime, there was one question for Lucas. Lucas, are you still on the line?
Yes, I am.
Yeah, there was one question for you. This is from Mike Alexander, and he was wondering to what extent wave speed is sensitive to changes in grid resolution in the variable grid runs.
I'm sorry, could you repeat that?
Sure. So Mike was asking, to what extent is wave speed sensitive to changes in grid resolution in variable grid runs?
We haven't seen very much of a wave refraction at the ends of these nested grids. It is possible, for the stretch grid, we see very little artifacting at all. Although in some aquaplanet runs, we have been able to demonstrate the appearance of spurious Walker-type circulations that don't otherwise affect the larger scale circulation. In the nested grid runs, if you do look hard enough, there's always nested grid artifacts, but they do not appear to be affecting our two-way testing simulations. Temperature nesting has reduced the artifacting.
And then I think there was, thank you, Lucas, and thanks, Mike, for the question. I think Justin maybe had a question for Ben. Justin, are you there?
Oh, yeah, I am here. And just the question was, I should probably know this, and I think I know part of the answer, but can you just describe in detail the interactive ensemble idea and the role of intrinsic ocean variability versus atmosphere variability for your last two slides?
Do you have a half hour, Justin?
No, not here.
So the basic idea is just to use ensembles, in this particular case, use ensembles of atmospheric realizations coupled to a single ocean model. And so at the air-sea interface, we're using 10 atmospheres coupled to a single ocean, and at the air-sea interface, we just take the ensemble mean of the fluxes to couple to the oceans. The idea is, can you, if you can control the amplitude of the intrinsic atmospheric variability that's independent of the SST, can you understand how much of the variability that's forcing? So that's the basic idea. And I know I went too fast over these plots, but we could probably sit down and chat about them for a couple of hours next time I visit. So
yeah, that'd be great. Thanks, Ben.
Yeah. Thanks for the question, Justin. Okay, so we've gone quite a bit over past 1 o'clock, so that's my failure as a timekeeper. I did want to spend a moment just showing what the results were from the 3 polls. So let me see if I can do this correctly. I'm going to share the results of the first poll with you all. Okay, so you should see the pop-up. The first question was in the computationally limited trade-off space between the areas below, which area holds the most promise for improving the skill of seasonal forecasts. And the results, you can adjust to the columns yourself. They're, at least on my screen, they're a little bit covered over in terms of the results. In terms of the percentages, it's counting no answer as one of the categories. So if you actually take that out, resolution was chosen 21% of the time, physics was chosen 46% of the time, modeling components were chosen 10% of the time, data assimilation and initialization was chosen 21% of the time, and one person chose ensemble size, so that's 2%. I'm wondering whether any of the speakers want to comment on this, if this is surprising to them, if this is expected that the most popular option would be physics and then resolution and data assimilation, and then improving the components or adding new components. Or you want to share your own thoughts on this?
This is Ben. I would just share one thought, is that physics and resolution are coupled. You can't, and I think Jim Kinter said this very nicely, and I think Justin also noted it too. I don't think you can separate the two very simply. You know, what physics you're ultimately using is going to be affected by the resolution and what processes you resolve. And so I think the two are intimately connected.
That's a really good point.
And I would absolutely have to agree with Ben and Jim on that point.
Okay, thanks. Any other comments on this from any of the speakers?
This is Justin. I know I showed many of the kind of advantages of the ocean and atmosphere resolution, but in my papers I also discuss, and I think Jim also mentioned it, a lot of the common biases in the coupled models are still there at different resolutions, including the ITCZ bias and so on. So when I've given this talk, longer version of the talk before, I've really said that research into the physics needs to be done in conjunction with the higher model resolution. You can't do one or the other, I think.
Okay. Thanks, Justin.
Dan, one other point. So very much what Ben and Justin said I agree with, but I'll also point out that part of the issue with increasing resolution and improving physics is this notion of tuning. Every time we change the physics in a given model, and this is typically done in standalone components, but it's probably better done in coupled simulations. Every time we change the physics, things either get better or worse, but usually worse. And then there's a period of retuning, which means adjusting tunable parameters to do a better job of matching the benchmarks that we use for validation of the model. And that turns out to be computationally, it's a big computational drain, because particularly if you're trying to do this with a high resolution model, what you end up seeing is that people do what's called the heroic simulation. They run the model at very high resolution once and then analyze the heck out of it, when in fact they should be doing a huge number of simulations in order to evaluate the sensitivity to parameter settings.
Okay, that's interesting. So it's the computational cost of doing all the testing?
Right. I mean, typically, you know, when you see people doing CMIP, for example, NCAR is at version number 115 or so of the CESM2, and that means that 115 versions have been tested with hundreds of years of coupled simulation and various settings of the tunable parameters in order to understand sensitivities of large-scale climate phenomena to those settings. So that turns out to be a huge computational cost during the development phase, and then, you know, when you get to the point where you're running reforecasts or climate change simulations, that's another computational cost, and both of them are non-trivial.
Yeah, they're a little bit hidden too. Okay, thanks for the comment.
And not very well documented.
Right. Okay, thanks for the comments on that question. I'm going to move to the next one. So this question was, let's see, to improve the seasonal prediction skill of global coupled models, it is more important to focus on increasing atmospheric resolution than oceanic resolution. The way this is phrased causes some issues in terms of the response, but basically it was fairly close to 50-50, so true was 44% and false was 56%. Again, 61% didn't answer the question. So either they were timid or were not engaged at this point. But I'm wondering again if there are any comments on these results from any of the speakers.
Well, this is Jim. Very much analogous to what Ben said on the last question. The two are linked. If you radically increase atmospheric resolution, the ocean at coarse resolution may not be able to respond to the higher level of gradients and information content coming from the atmosphere, and vice versa. So really, there is and we've seen this in coupled reforecasts that we've done, where we made enormous increases in atmospheric resolution, and the coupled model kind of went meh because the ocean model was insufficiently capable of responding to the high resolution information from the atmosphere.
Okay. Yeah.
Dan, this is Paco. We've been testing the relevance of well, either atmosphere or ocean resolution, and after playing a bit with this in a seasonal focus context, the point is not which one is the most relevant, but which is the right combination between the ocean and atmosphere resolution given a certain amount of computational resources that you have. So this is the actual combination of the two that is well, it's unknown, and it's not easy to tune this thing precisely for the same reasons that I think it was Jim who was talking about how expensive it is to tune parameters when you go for those heroic resolutions.
Yeah. Yeah, Heather was just pointing out that, that's kind of embedded in the option of false here. So some of these answers of false may not have been just choosing bimodally between, atmosphere and ocean, but also choosing the option that I think you and Jim are both suggesting as well.
That's another thought I had about it, and a reason I didn't respond to that one was what skill you're talking about, and whether it's a particular variable or whether it's regional or global. And I'm thinking that I can imagine maybe some regional improvements with higher ocean resolution, and I think Ben was showing some examples of South America that hinted at that, as opposed to global improvements in global skill. I'm not so sure about whether that kind of thing would improve the global skill, but you get some regional improvements.
Yeah, that's a really good point. Yeah, especially in the context of Ben's talk. Okay, and then moving on to the final question. So this question was, what atmospheric resolution threshold increase will give the greatest boost to the skill of subseasonal to seasonal predictions from global coupled models? And again, about 60% of the attendees were non-responsive on this, but still there's some kind of clear results here. There's basically a cascade from top to bottom. So the top category, 100 to 50, 31% chose that. 50 to 25 kilometers, 19% chose that. 25 to 10 kilometers, 13% chose that option. And then 2 people each chose the 10 to 5 kilometers and the 5 to 1 kilometers. 8 people, or 25%, chose that resolution is not the answer. So 32 responses. And again, any comments on this question or the results? Is it surprising to any of you that the top category was most popular?
Not to me.
Yeah, this is Jim. I'm not surprised. We see a big improvement when you get away from the 1 degree, 100-kilometer resolution, and then there are diminishing returns, which I think is largely associated with our, the lack of retuning as we go to higher resolution.
Mm-hmm. Yeah. So your presentation has an effect.
Or the fact that the physics is now less compatible with the higher resolution. Yeah.
Yeah.
Okay. Okay, well, I want to thank everyone for hanging in here. I mean, we've gone about 25 minutes over or 20 minutes over at this point, but I think it was really interesting to talk about the poll results, and I really appreciate the speakers hanging around for a bit and commenting on the results and reflecting on them a bit. I'll think about, whether to do this again. If anyone that attended this webinar has any comments on the polling or other elements of the webinar, please shoot me an email and let me know. I'm happy to rethink this or just scrap it. I thought it was kind of interesting to see these results, and I think a neat way to keep people engaged with the webinar as well, and maybe focusing on the talks also. So I want to thank the speakers. This was really a great session, and I enjoyed every one of your talks, and I appreciate you taking the time. Paco, thank you for hanging on the line so late, your local time. We have another webinar coming up on March 28th, and this is on the topic of water modeling, so unified water modeling. There are a variety of speakers covering different elements of the water modeling mission of NOAA, so anything from droughts to floods to marine fisheries issues. So please try to join for that. That's from 12 to 1:30 p.m. We'll post the recording of this webinar and the slides on the website probably within the next couple of days or so. And I'm going to leave it with one more poll question that we didn't get to during the actual webinar itself. This question is on CMIP 6. So it wasn't really explicitly relevant to any of the talks in particular, but basically the question is asking, let's see, among those listed below, what phenomena will most significantly benefit from the increased resolution of CMIP 6 era models, which, talking about resolutions of approximately 1 degree in the atmosphere and less than 1 degree in the ocean. And you can choose up to 3 answers here, so feel free to choose 3 of these that you think will really benefit from the type of resolution that CMIP 6 models in the DEC experiments at least are going to be targeted at. And I'll post the results for this on our website. We won't discuss these here, but I'll leave this open for a couple of minutes so you can choose to respond, and then we'll put the results up on our webinar website. So anyhow, thank you so much for joining, and thanks again to our speakers, and hopefully you'll be able to join again on March 28th, which is a Tuesday. Take care. Thank you.
Thanks, Dan.
Thanks, Dan.
Thanks, Dan.
Thanks.